Additivity of Integration Intervals. Okay, so let's move on to a really useful property of definite integrals. This slide introduces what we call property p subscript 2. Think of it as a tool that allows us to simplify integration. Essentially, this property lets us take a single, potentially complicated integral, one that calculates the area under a curve from a starting point, A, to an ending point, B, and break it down into smaller, more manageable integrals. We do this by choosing an intermediate point, let's call it C, within that interval. What property p subscript 2 states is that the integral from A to B of a function f of x with respect to x is equal to the sum of two integrals. The integral from A to C of f of x with respect to x plus the integral from C to B of f of x with respect to x. Geometrically, what's happening here is that we're calculating the total area under the curve by adding up the areas of two separate sections. The first section is the area from x equals up to x equals c, and the second section is the area from x equals c up to x equals b. It's like dividing a larger area into smaller, easier to calculate pieces. This will be particularly helpful when we encounter functions defined in pieces or functions with absolute values, as we'll see in the upcoming slides. So, keep this idea of breaking down the integral into smaller parts in mind. It's a fundamental technique in calculus. The mathematical statement. Okay, so let's move on to formally stating this additivity property, which we've already discussed geometrically on the previous slide. This slide gives us the mathematical notation. Here, we're saying that for any function f of x, as long as it's integrable, meaning we can find the area under its curve, within the interval from a to b, then this property holds true. Now, let's look at the property itself. The integral from a to b of f of x dx, that's read as the integral of f of x with respect to x, from a to b, is equal to the integral from a to c of f of x dx, plus the integral from c to b of f of x dx. Essentially, what this equation is saying is that the area under the curve of f of x from a to b can be found by adding together the area under the curve from a to some intermediate point c, and the area under the curve from c to b. Think of c as a point we choose within the interval from a to b to split it into two smaller intervals. Now, let's break down each component of this equation. Number 1, the integral from a to b of f of x dx. This represents the total integral, the total area under the curve of f of x, across the entire interval from a to b. Number 2, the integral from a to c of f of x dx. This is the integral, or the area, from the starting point of up to our intermediate point c. And finally, number 3, the integral from c to b of f of x dx. This is the integral, or the area, from our intermediate point c to the endpoint b. So, the property simply states that the total area is the sum of these two smaller areas. This will be incredibly useful when we encounter functions that are defined differently over different intervals, like absolute value functions or piecewise functions, which we'll see in the upcoming slides. Remember, C just needs to lie between A and B for this property to work. Real-world analogy. Okay, so let's move on to slide 3. This slide uses a real-world analogy to help solidify our understanding of the additivity of integration intervals, what we've been calling property P2. Think about a road trip. Imagine you're driving from city A to city B, but there's city C located somewhere in between. To find the total distance of your trip, what do? You wouldn't try to measure the distance from A to B directly, right? Instead, you decalculate the distance from city A to city C, and then add that to the distance from city C to city B. The total distance is simply the sum of those two individual distances. Now here, S where the connection to calculus comes in. In calculus, instead of thinking about distance, we're thinking about the area under a curve. That's what our definite integral represents. And instead of cities, we have our limits of integration. So, city A corresponds to the lower limit of our first integral, city and C is our intermediate point, and city B is the upper limit of our second integral. Just like we added the distances between the cities, we add the areas under the curve over each of those subintervals. This is exactly what property P2 allows us to do. We're breaking down a larger, potentially complicated integral into smaller, more manageable pieces. This analogy is important because it provides an intuitive understanding of why this property works. It's not just a mathematical trick. It reflects a fundamental principle about accumulation, that the total accumulation over an interval is the sum of the accumulations over its subintervals. Keep this analogy in mind as we move forward, because on the next slide, we'll start looking at when and how to actually apply this property to solve integration problems, specifically with functions that have different definitions over different intervals. When to use this property. Okay, so let's move on to understanding when we actually use this additivity property, what we've labeled as property P2. This slide outlines the essential scenarios where breaking up that integral into smaller pieces, as we discussed on the previous slides, becomes really helpful. First, we have piecewise functions. Now, remember, a piecewise function is a function defined by different formulas over different intervals. So, if you have a function that changes its rule halfway through the interval you're integrating over, you must split the integral at that point where the rule changes. We'll use property P2 to integrate each piece separately and then add the results. Next, we have absolute value functions. These are a bit tricky because of the sign changes. The absolute value of an expression, like the quantity x minus 1, changes from positive to negative or vice versa when the expression inside the absolute value equals 0. So, we need to split the integral at the points where the function inside the absolute value is equal to 0. This is because the absolute value essentially defines a piecewise function itself, a positive part and a negative part. We saw this coming up in our example on the following slides, where we dealt with the absolute value of x minus 1. Finally, we have simplifying complex limits. Sometimes, you'll encounter integrals with limits that are a bit complicated. Splitting a large interval into smaller, more manageable subintervals can make the integration process much easier. It's like breaking down a big problem into smaller, more solvable parts. So, keep these three scenarios in mind: piecewise functions, absolute value functions, and simplifying complex limits. These are the times when property P2 will really come in handy, and we'll see it in action as we work through more examples. Step-by-step application, example. Okay, so let's move on to applying this additivity property, which we've denoted as property P2. As you recall from the previous slides, this property allows us to break down a single integral into multiple integrals over smaller intervals. We're going to illustrate this with a concrete example. We want to evaluate the definite integral of the absolute value of x minus 1 from 0 to 3. That's written as integral from 0 to 3 of the absolute value of x minus 1 with respect to x, and we'll use property P2 to do this. Now, step 1 is to identify the critical point. Remember, the absolute value function changes its behavior, its algebraic form, at points where the expression inside the absolute value becomes 0. So, we need to find the value of x that makes x minus 1 equal to 0. Solving that simple equation, x minus 1 equals 0 gives us x equals 1. Therefore, our critical point, which we'll call C, is 1. Step 2 is where we actually split the integral. We're going to break up the integral from 0 to 3 into two integrals, using our critical point, C, which is 1, as the dividing line. So, the integral from 0 to 3 of the absolute value of x minus 1, with respect to x, becomes the integral from 0 to 1 of the absolute value of x minus 1, with respect to x, plus the integral from 1 to 3 of the absolute value of x minus 1, with respect to x. Notice how the limits of integration align correctly. The upper limit of the first integral is 1, which matches the lower limit of the second integral. This is crucial for the property to hold. In the next steps, we'll remove the absolute value and integrate each of these simpler integrals separately. Step-by-step application, continued. Okay, let's move on to step 3. Remember, in the previous steps, we set up the problem and identified our critical point at x equals 1. Now, we need to actually evaluate the integral, and to do that, we need to get rid of those absolute value signs. The absolute value function, as you recall, outputs the magnitude or non-negative value of whatever is inside it. So, the expression inside the absolute value can be either positive, negative, or 0. The sign determines how we remove the absolute value. Let's consider the interval from 0 to 1. If we pick any value of x between 0 and 1, say x equals 0.5, then x minus 1 equals negative 0.5. So, within this interval, the expression x minus 1 is negative or 0. Therefore, when x is between 0 and 1, the absolute value of x minus 1 is simply 1 minus x. Think of it as flipping the sign to make it positive. Now let's look at the interval from 1 to 3. If we pick any value of x between 1 and 3, say x equals 2, then x minus 1 equals positive 1. So, within this interval, the expression x minus 1 is positive or 0. This means that the absolute value of x minus 1 is just x minus 1. No change needed. So, after removing the absolute value signs based on their respective intervals, our original integral transforms into the sum of two simpler integrals. We now have the integral from 0 to 1 of 1 minus x, plus the integral from 1 to 3 of x minus 1. This is a crucial step because it allows us to apply the standard rules of integration to each part separately. In the next step, we'll actually perform those integrations, and then we'll be just one step away from our final answer. Does that make sense so far? Step-by-step application, integration. Okay, let's move on to step 4, where we actually perform the integration. Remember, in the previous steps, we split our original integral and removed the absolute value signs, resulting in two simpler integrals to evaluate. So let's start with the first part. The integral from 0 to 1 of 1 minus x, with respect to x now, applying the power rule for integration, the integral of 1 with respect to x is simply x, and the integral of x with respect to x is x squared divided by 2. Therefore, the indefinite integral of 1 minus x is x minus x squared divided by 2, plus our constant of integration, which we don't need to write out for definite integrals. Now, we evaluate this from our lower limit of 0 to our upper limit of 1. This means we substitute x equals 1 into our result, and then subtract the value of the result when x equals 0. So, we have 1 minus 1 squared divided by 2 minus 0 squared divided by 2. This simplifies to 1 minus 1/2 minus 0, which equals 1/2. Now, let's move on to the second part. The integral from 1 to 3 of x minus 1 with respect to x again, using the power rule, the integral of x with respect to x is x squared divided by 2, and the integral of 1 with respect to x is simply x. So, the indefinite integral of x minus 1 is x squared divided by 2 minus x, plus our constant of integration. Evaluating this definite integral from 1 to 3, we substitute x equals 3 into our result and subtract the value of the result when x equals 1. This gives us 3 squared divided by 2 minus 3 minus 1 squared divided by 2 minus 1. That's 9 divided by 2 minus 3 minus 1/2 minus 1. Simplifying, we get 9 divided by 2 minus 6 divided by 2 minus 1/2 minus 2 divided by 2, which is 3 divided by 2 minus divided by 2, which equals 3 divided by 2 plus 1 divided by 2, giving us a final result of 2. So, we've now successfully integrated both parts of our split integral. In the next step, we'll simply add these two results together to find the total value of the original integral. Step-by-step application, result. Okay, so we've reached the final step in evaluating this integral. As you recall from the previous slides, we were working on evaluating the integral of the absolute value of x minus 1 from 0 to 3, and we cleverly used property P2, the additivity of integration intervals, to break it down into two simpler integrals. Now, step 5 simply asks us to sum the results we obtained from integrating each of those smaller intervals. Let's look at what we have. We calculated the first integral from 0 to 1 to be 1/2 or 0.5, and the second integral from 1 to 3 we found to be 2. Therefore, the total value of the original integral is simply the sum of these two results. So, 1/2 plus 2 equals 2 and 1/2, or, expressed as an improper fraction, 5/2. So, the final answer to the integral of the absolute value of x minus 1 from 0 to 3 is 2.5, or 5/2. And with that, we've successfully evaluated the integral. Remember, this technique of splitting the integral using property P2 is particularly useful when dealing with functions like absolute values or piecewise functions, where the function's definition changes within the interval of integration. We'll be reinforcing this concept as we move forward, and you'll see it pop up again when we tackle more complex integration problems. Now, let's move on to the next slide, where we'll discuss some common mistakes to avoid when applying this property. Common mistakes to avoid. Okay, let's move on to slide 9. This slide highlights some common mistakes students make when applying the additivity of integration intervals, property P2, as we've been calling it. Paying attention to these will save you a lot of frustration. First, let's talk about incorrect split points. Remember, the whole point of splitting the integral is to break it down into sections where the function's definition doesn't change. What I mean by that is, if you have a piecewise function, or something like an absolute value function, you need to split at the points where the formula inside the integral changes. For example, with absolute values, you split at the points where the expression inside the absolute value becomes 0. Those are the roots. If you split at the wrong point, you're essentially mixing definitions and getting a wrong answer. Next, we have sign errors in absolute values. This is a really common one. Remember that the absolute value of something, let's say the absolute value of x minus 1, gives you the magnitude or the positive value of that expression. So, if you're integrating an absolute value function and you're on an interval where the expression inside the absolute value is negative, you must negate it when you remove the absolute value signs. Otherwise, you'll be integrating a negative value when you should be integrating a positive one, leading to an incorrect result. We saw this in our example on the previous slides, where we changed x minus 1 to 1 minus x when x was less than 1. Finally, let's address limit confusion. This is a bit more mechanical, but still important. When you split the integral, make absolutely sure that the upper limit of integration of your first integral matches the lower limit of integration of your second integral. In our formula, integral from a to b of f of x dx equals integral from a to c of f of x dx plus integral from c to b of f of x dx. Notice how the c appears in both integrals, linking them together. If those limits don't match up, you're not actually integrating over the correct intervals, and your answer will be off. So, keep these 3 points in mind as you practice. We'll wrap everything up on the next slide with a quick review of the key takeaways. Key takeaways. Okay, let's recap everything we've learned about the additivity of integration intervals, which we've been calling property P2. This slide summarizes the key takeaways. First, remember that property P2 essentially allows us to break down a single, potentially complicated definite integral into a sum of simpler integrals. Specifically, the integral from a to b of f of x dx, that is, the integral with limits a to b of the function f of x with respect to x, is equal to the integral from a to c of f of x dx, plus the integral from c to b of f of x dx. Think of c as a point within the interval from a to b, allowing us to split the integration. Now, why is this useful? Well, as we saw in our example with the absolute value function, this property is a primary tool when dealing with functions defined in pieces, what we call piecewise functions, or functions with absolute values. These often change their definition or algebraic form at certain points, and property P2 lets us handle those changes neatly. Speaking of changes, that brings us to the next point. The value c, the point where we split the integral, is crucially the point where the integrand, that's the function inside the integral, f of x, changes its algebraic form. In the absolute value example, that was where the expression inside the absolute value became 0, causing the function to switch from positive to negative. Finally, and this is a good way to visualize it, remember that the definite integral represents the area under the curve. So, property P2 is saying that the total area under the curve from A to B is simply the additive sum of the areas under the curve from A to C and from C to B. This is a powerful technique, and mastering it will make integrating more complex functions much more manageable. We've built up to this through the examples, and now you have a solid understanding of how and when to apply it.